These programs are distributed under a Creative Commons Attribution, Non-Commercial, No Derivatives license. You may copy and distribute these programs free of charge. You may not sell them, and you may not alter them. These programs are part of a study examining the value of podcasting as a medium for medical education. If this is the first time you are viewing a program in this optics series, send an email to jyoungmd@gmail.com with your name, position, institution, and city, state or province, and country. Thanks, and enjoy the podcasts. Simple magnifiers are probably the biggest misnomer in all of optics because there's nothing simple about them. I'm going to explain first what you sort of need to know to spit back to people when they ask you questions. And then I'm going to lay the truth on you. We're told that the magnification that we get from a simple magnifier is equal to d over 4. Now, what does this mean? What's a simple magnifier? Let's say that you go into Jack's 99-cent world and you see a magnifying glass there, and the magnifying glass says magnifies 5 times. What does that mean? What does it mean it magnifies 5 times? We can determine what the magnification of a lens is by taking a particular reference distance and then saying, well, the magnification at this reference distance is X. The reference distance that is conventionally taken is 25 centimeters or 1/4 of a meter, producing the formula d over 4. So that if you have here's the question that you're typically asked. An emmetropic ophthalmologist is looking in the eye of a patient with a direct ophthalmoscope in which no lenses are set. We're just using it as a light source. And the ophthalmologist sees the optic nerve magnified. Now, let's say it's a 1 millimeter optic nerve, which would be a small optic nerve. How many millimeters large does the ophthalmologist observe that optic nerve to be? And the way that you're to go about this problem is say, well, what is the dioptric power of the entire anterior segment of the patient's eye? And the answer is it's about 60 diopters, about 45 diopters from the cornea, about 15 from the lens, plus or minus. And 60 over 4 is 15. So the optic nerve must look 15 times larger. So if it's 1 millimeter in the patient's eye, it's going to look to the observer to be 15 millimeters. You can stop the lecture here and just go on to the next topic because that's what you have to know about simple magnifiers. However, looking at this problem even briefly will tell you that this approach to it is just stupid. First of all, there's no eye that's 25 centimeters long, so the reference distance with the eye is meaningless. But secondly, even when we use the reference distance, it doesn't always work. Let me show you what I mean. Let's say that we get a lens that's a plus 10 diopter lens, right? A nice magnifying lens, and we're going to use it at our standard reference distance of 25 centimeters. Let's see what happens. We're just going to kind of talk this through. 25 centimeters is 1/4 meter. So the rays of light that hit this lens coming off of the candle are going to have a divergence of what? Well, 1/4 meter to the left is where the rays of light converge. 1/4 meter means that the absolute value of the divergence is 4. To the left means that it's minus, so it's minus 4. Minus 4 plus 10 is equal to plus 6. It means that the rays of light converge 1/6 of a meter to the right. Now, the base of this triangle, if we're trying to do central ray tracing, is 1/6 of a meter. And the base of this triangle is 1/4 meter. So not only is this lens not magnifying at the reference distance, it's minifying and inverting. So it's obviously a much more complicated situation than d over 4 would have us think. In order to understand what's going on with simple magnifiers, we need to define 2 points. One point is f. It's the primary focal point. In this case, it's at a distance of 0.1 meters to the left of our plus 10 diopter lens. The second point that I'm going to bring into play is 2f. And 2f is 2 focal lengths from the lens. It's twice as far as f is. And I'm going to tell you that it is very important where the object falls relative to these 2 reference points. Let's work this through. Let's take the example now of an object that is an ant that is 0.08 meters from the lens. So this is between f and the lens. You'll remember f is 0.1 meters from the lens. And we're going to apply our newly found skills at vergence and central ray tracing, and we're going to work this all through, and we're going to see what is going on in this case. I'm not going to draw the vergence lines here because it's just going to get too cluttered. But you know that the rays of light coming off of this ant are going to strike the lens with a vergence of, well, 1 over 0.08, and it's going to be minus because the rays of light are converging at the ant. That's where they're starting out. So the vergence of the rays of light striking the lens, the vergence is minus 12.5. The lens is a plus 10 lens, so the vergence of the rays of light coming out of the lens, minus 12.5 plus 10, is equal to minus 2.5. Minus 2.5 means that the rays of light converge 1 over 2.5 meters, and minus means to the left. So that's going to be 0.4 meters, and that's where the image is. And now we're going to draw our central rays. And one ray through the head of the ant and one through the middle there. And we can see that our image is there, a great big ant. Now, what is that ant? That ant is magnified. It's upright. It's also virtual. I'm sure that you didn't think of that in terms of when you use a magnifying glass that what you're looking at is a virtual image. But it is, because it's offsides with respect to the lens. So upright, magnified, and virtual. That's our usual experience with magnifying glasses. Now, let's take the case of where the ant is between f and 2f relative to the lens. So it is greater than 0.1 meters but less than 0.2 meters. So we're going to put our ant at 1/8 of a meter from the plus 10 lens. We're going to see what happens. The vergence of the rays of light striking the lens from this ant that's at 1/8 of a meter from it are obviously going to be minus 8. Minus 8 plus 10 is equal to plus 2. Plus 2 means that the rays of light converge 1/2 meter to the right. We're going to draw out our central rays, and we see that the image is going to be inverted. We also see that the base of the triangle to the right of the lens is larger than the base of the triangle to the left, so it is going to be magnified. So the image is what, and what? It is inverted, magnified, and real, because it's to the right of the lens. Now, let's move the ant beyond 2f. This time we're going to put the ant at 0.5 meters from the lens. You remember 2f is only 0.2 meters from it. And we're going to plot things out. The vergence coming in is going to be minus 2. The vergence going out is going to be plus 8. The image is going to be formed, therefore, 1/8 of a meter from the lens. We'll draw our central rays. And we see that the ant is upside down and is minified and is real. So this is certainly not typically our experience with magnifying glasses. And certainly not our idea of what would be going on using the simple-minded d over 4 formula, that depending upon where an object is, a plus lens can result in one of 3 outcomes. The image can be upright, magnified, and virtual. It can be inverted, magnified, and real, or inverted, minified, and real, depending upon where we are relative to f and 2f. Now, you can try this if you have a plus 20 lens in your pocket now. And if you bring that lens closer than 5 centimeters, meaning closer than f, to, let's say, a coin on the table, you'll see that the coin is upright and magnified. You can also get the sense that it's virtual because it looks like it's in a plane that's deeper than the top of the table. If you draw the 20 towards you so that the coin is, let's say, 8 centimeters from the lens, the coin will flip around. It will be magnified. It'll be hard to hold the lens steady, in fact. It'll be magnified, and it may be difficult to see. You should back up from the lens as much as you can. And the reason is that the aerial image being formed, that real image, is being formed close to your face, and you need to accommodate quite a bit in order to see it. And then if you pull the lens even further back, more than 10 centimeters back from the coin will be inverted and minified and will be easier for you to focus on. You won't need to accommodate as much because the image will be closer to the surface of the lens. So try these neat tricks out. Minus lenses really are simple. Minus lenses only do one thing. The object is shown here. The image is shown here. It's always like that. When used as a single lens, a minus lens will always make things upright, minified, and virtual.